Dear learners, welcome to today's session. In this video, we are going to discuss one of the most commonly used transistor circuit, the common emitter transistor as an amplifier. So what is a common emitter transistor? It is a transistor configuration in which the emitter terminal is common to both the input and the output junction. This arrangement is most commonly employed because it provides high voltage gain. Now let's talk about the electronics of the common emitter amplifier. What it consists? It consists of a biasing circuit which consists of two resistance R1 and R2. So basically this biasing used here is voltage divider biasing, and it is provided at the base of an NPN transistor apart from this. There is RE, which is the emitter resistance connected, and RC, that is the collector resistance. And for the biasing we have provided VCC. Also there are capacitor CC1 and capacitor CC2, which is called as the coupling capacitor. We will be discussing it shortly, what it actually is. And the output is taken from the load resistance RL. The signal which we are to amplify is given as the input Vi. So this is the drawing of common emitter amplifier. Now let's understand the role of each component one by one. The first component we are going to discuss is the coupling capacitors. So here two coupling capacitors are used, which are denoted by CC1 and CC2. Now these are also called as the blocking capacitor. Now we know that the reactance of a capacitor is given by Xc, which is equals to 1 by iota omega c, where omega is the frequency. And for DC, this omega is 0 and hence reactance is infinity. So we can say that capacitor blocks DC and it allows AC to pass through it and allows AC, because the reactance is finite for the AC. So this is why this CC1 ensures that the DC from the biasing circuit, here we have provided VCC, so there will be a DC component, and this CC1 blocks the DC to go from here to this input signal and allows the AC to pass through it. Similarly, this CC2 also blocks the DC from this VCC to come into the output signal. So hence these are called as the blocking capacitors, as they block the DC, and they're also named as the coupling capacitor. The second component is called as CE, known as bypass capacitor. So this capacitor provides an alternative path for the emitter current. Now we can see that here is the emitter current. So if we join a capacitor here and name it as CE, the emitter current will have an alternative path to go from here through this side to here, like this. Instead of following the path through resistance, it will follow the path through capacitor, but for this the condition is that this capacitive reactance should be less than 1 by 10th time of the emitter resistance. Now what will happen here, that if there is no current passing through this, so there will be no potential drop across it, and all the output voltage will be appeared at VCE. So for example, we have amplified the input signal of 1 volt and it is amplified to 5 volt. So at output there should be 5 volt voltage drop, but if the current IE flows through the resistance, there will be some voltage drop, for example 2 volt at this resistance, and the output there will be only 5 minus 2, that is 3 volt, that will appear on the output. So our output will be reduced, and we don't want that. So we want that there should be an alternative path for the current to pass, and that is given by this capacitor CE. So the requirement here is that XCE should be less than 1 by 10th of RE. So the third component we are going to discuss is the voltage divider bias, that is R1 and R2. These resistors fix the bias voltage and provide the stabilization of operating point. So the stability of operating point, which is a must thing for a better operation of the transistor as an amplifier, the biasing is used. So this biasing helps in the stability of operating point. Then at last we are having fourth component, which is our input and the output component. So input is provided by Vi, which is a small input signal. Say it is a sound signal from the microphone which we need to amplify from the speaker, and the output is taken from the load resistance RL as shown in the figure also. Now let's move to another very important feature of the common emitter amplifier, that is the phase shift between the input and the output signal. Suppose the input signal is sinusoidal, so we are having Vi as this. So when the input signal is increasing, that is we are talking about this half, the current IB here also increases because of the Ohm's law. V is directly proportional to I. So as input voltage is increasing, current is increasing, and because of the transistor action, this increase in IB causes increase in the collector current. We know that the collector current, which is IC, is directly proportional to the input current. In fact, it is given by beta times the input current, where beta is the current gain. So IC also increases. So I'm writing here that with increase in Vi, IB increases, and hence IC also increases. Now IC flows through the collector resistance RC. It is flowing here. So the voltage drop across RC also increases with the increase in VC, increases with the increase in IC. So the total voltage VCC which we have provided, so VCC is equal to, by the Kirchhoff law in this loop, VCC is equals to VC plus the VCE, which is actually our output voltage, and there is no potential drop across here because we have made the current to pass through this bypass capacitor. So the output voltage, which is VCE, is given by VCC minus VC, where VC is VCC minus IC RC. So we can say that with an increase in IC, there is a decrease in VCC, because the term containing IC is being subtracted from a constant term. This is a constant voltage we have applied from outside. So V output, which is equals to VCE, it decreases with increase in IC, and we know increase in IC is the result of increase in input. So at the end, what we have concluded, that with increase in VI, that is input signal, there is a decrease in V output, that is our output signal, because IC is increasing because of VI increases. So VI increases and V output decreases. Hence there is a 180-degree shift in the input and output. So we can also say that the output is inverted with respect to input. So here we were having input like this, and the output will come like this. It is amplified, the amplitude is high, but the phase is shifted by 180-degree. At the end, let's discuss the characteristics of common emitter transistor. The input impedance of the common transistor is around 2 kilo ohm to 5 kilo ohm. The output impedance is quite high, which is around 50 kilo ohm. The voltage gain, which is the common characteristic of this common emitter transistor, which is very high and around 1500. The current gain is moderate, that is 300, and just we have discussed that the phase shift of 180-degree is introduced between the output and the input signal. So that's it about